Hi, this is Josh White with JW Math Tutoring, and today's video is going to focus on the technique of backsolving, and specifically how you can use that technique to solve problems on the math sections of the SAT, both no calculator and calculator sections. If you like this video, please be sure to click the like button and of course subscribe to my channel and sign up for notifications so you find out whenever I post another excellent math related video. But with that said, let's go ahead and get started on how you can use backsolving to solve math problems on the SAT.
But life is a dream the calculus could never predict.
One thing just to be aware of before I start going through the video on backsolving is that there will be a list of problems that from previously released tests that you can practice with to get additional practice on using the technique of backsolving. So it'll basically have the test number, problem number, and then also it'll have the answers to check them against as well. So as I mentioned, this video is going to talk about the strategy of backsolving and how you can use that to solve problems on the SAT. So what is backsolving and why would you do it? Backsolving, or as it's also known, plugging in the answers, is basically a multiple choice answer strategy that involves generally using the given answer choices to solve a problem. And the way you do that is by basically working out the problem and matching criteria or information that is given in the problem, and this allows you to determine which answer is the correct answer. I mean, essentially, in a lot of cases, it's working the problem kind of backwards to figure out which answer has to be the correct answer. Why should you learn backsolving? Why should you use it? Well, there are several reasons. First, it can a lot of times be quicker than solving a problem the traditional way, the way you might be taught how to do it to solve it in school. Second, it can be sometimes a lot easier to solve the problem using these backsolving techniques rather than the traditional way. And the third case is, you might not know how to solve the problem the traditional way. Either you never learned it, or it just might be too difficult or too complicated, but using backsolving might be easier. So those are several reasons why you should want to learn backsolving and why you should want to possibly use it when possible to solve problems on when there are multiple choice answers. Now, when do you know how to use it and how exactly does it work? So there are some clues you can look at in determining when to use backsolving. The first is when you have a question that's asking for just a single quantity. What is the length of the rectangle? Or what is the value of x? As compared to problems where it might ask for the sum or the difference or the product of, say, two numbers or two variables. So that's one clue or one thing to be aware of. Another common problem type where you can use backsolving is when you have equations or inequalities, just essentially with one variable that you're asked to solve. And then another problem that you see where backsolving can sometimes be useful is when you have something asking for the highest or lowest amount, maximum or minimum amount of some specific quantity. Now, how exactly does it work? So let's go ahead and take a look at some example problems and we'll see how you can use the answer choices to work these problems sort of backwards and get the correct answer. The first example I'm going to take a look at is from the May 2022 QAS. It's from section 3, which is the no calculator section, and it's problem number 4. So if you look at this problem, there are two triangles here. And it turns out these triangles are similar because it tells us in the problem that angles ACB and ECD are congruent. So this angle and this angle right here are congruent to each other. Those two angles, that pair of congruent angles along with the right angles makes these two triangles similar by the AA similarity postulate. All right, so since they're similar, that means that the ratio of their sides will be proportional. So basically, the smaller triangle is half the size of the larger one, or all the sides are half the distance, half the length of the larger ones. Or the larger one is twice the smaller one, however you want to look at it. So it tells us here that AE, this entire thing, is 15. And it says, what is the value of CE? So here's how I would use back solving, or how you could use back solving to solve this problem without necessarily setting up any equations to solve. So say CE is 4. Okay? Then we should know or recognize that AC has to be 2. And in that case, how long is AE? Well, 2 plus 4 is 6. Is 6 equal to 15, which is the information that's given in the problem? No, it is not. Therefore, this answer is wrong, and we would move on to the next answer choice. And then we keep checking answer choices. So for example, this is now 5, and AC would be half of that, which would just be 2.5. Now if you add them together, do those two sides, or two sides of the triangles equal 15? No, cross it out. Next we have 8, so this side is now 8, and this side is 4. 8 plus 4 is 12. Does that equal 15? No. So by process of elimination, we know the correct answer is going to be D, but just to check it, if this side CE is 10, then the other side, its corresponding side, AC, has to be half of that, or 5. 5 plus 10 equals 15. This one checks. So the correct answer to this problem is letter D. Again, an example like this, it might not be any quicker or easier to solve this using back solving, but I just wanted to use this problem to kind of demonstrate the technique and show you, how the process works. And basically the whole idea is, it's like I'm taking the answer choices, I'm plugging them into the problem, and then I'm looking to either, basically for the correct answer, I'm going to confirm some piece of information in the problem, which in this case, it's that AE equals 15. For all the wrong answer choices, I'm basically contradicting that piece of information. Now let's take a look at another example. This is from the College Board's Practice Test 9, which is one of the 8 practice tests that they release for free on their website. It's also from section 3, the no calculator section, and it's problem number 11. So here you have an equation, and we want to know all the values of x that satisfy this equation. So the traditional way to solve this would be to go ahead and cross multiply, and then once you have that, you end up with a quadratic equation, and then you can solve that either by factoring or quadratic formula or whatever method you want. However, that is a fair amount of work and could take a little bit more time than you may want. So I'm just going to show how you could solve this one by using back solving, by just plugging in the answer choices and seeing which of these values work. So I'm going to start with letter A, and I'm going to start with 0. So when I plug that in, notice I just get 0 over 0 minus 3, and 2 times 0 is 0 over 2. So on the left side, I get 0. Now this is just negative 3. So notice I get 0 equals 0. That is a true statement. Therefore, 0 is one of the values of x that satisfies this equation. Because when you have an equation, the numbers that you plug in for it should give you the same value on both the left and the right in order to be a solution to that equation. Since I know 0 works now, I can automatically eliminate C and D because they do not have 0 in it. So now I'm just left to check basically 2 and 4. One of them is going to work, one of them isn't going to work. So now I'll just go ahead and check 2, and I get 2 over 2 minus 3, and then 2 times 2 is 4 over 2. So on the left side, I get 2 over negative 1. On the right side, I get 4 over 2, which is just 2 over positive 1, or 2. So I get negative 2 equals positive 2. Notice these two numbers are not equal. Therefore, 2 is not a solution to this equation here. It does not satisfy the equation. So I would cross it out, and the correct answer is going to be letter B. Now, just to show you real quick, if you went ahead and plugged in 4, you would get 4 over 4 minus 3, which is 1 on the left. On the right, you would get 2 times 4, which is 8, over 2 on the bottom, and 8 over 2 just reduces to 4 over 1, so we get the same number on both sides of the equation, and we can therefore conclude, yes, 4 is one of the other values that satisfies it. The next problem we're going to look at now is from the March 2022 QAS. It's from the calculator section, or section 4, so we're going to use a calculator. And it's problem number 15. Basically, you are given a table here with some values, basically for age, which is the variable A in the formulas below, and the amount of money, which is just D. And so really here you have a bunch of points, essentially like x and y points, or here they're A and D in these formulas, and you're trying to find which equation is the correct one. So this one you could back solve by just taking these points, or taking one of them ideally, and plugging them into the various formulas here and seeing which one it works in. Hopefully it only works in one, and we know that's the correct answer. If it works in two, then we just have to pick a second point and repeat the process. So I'm going to start with this one right here. The reason I'm not going to start with the one at the top, 2542, is because when they design these tests, a lot of times they assume that you'll start with the first point that you see, or the first one at the top, and so they'll make multiple answer choices that this first point will work on. I'm going to pick this one in the middle, and hopefully this will only work on one of them, so I don't have to do any repeating. So all I'm doing is I'm taking the A value and I'm just plugging that in, to each of these formulas on the right, and then I'm saying, do I get my output that matches the D column, or in this case 26. So for the first one, it's just negative 2 times 33 plus 92. Okay, I get 26. So far, this one appears to check. I'll keep it, but I do want to check the others just to make sure. So now I have negative, and I'm just going to, actually, I'll put the whole thing in parentheses. So I have negative 1/2, and then times the 33, and then plus 92. I get 75.5. That clearly does not equal 26, so now I move on. 2 times 33 minus 8. I get 58. That is not equal to 26. And then the last one, 2 times 33 minus 40. Okay, I get 26. So at least so far I found two potential correct answers. So now I just have to repeat this with a different point. So whatever, I'll just move to the next point below it now, 3522. So I'm going to repeat, let's see, the first one, negative 2 times 35 plus 92. I get 22. This one checks again, so it's looking likely that it's going to be answer choice A, but still don't know for sure. And now I'll just do 2 times 35 minus 40. Okay, now I get 30. This one is obviously wrong. It's not equal to 22, so the correct answer here is letter A. Now, it's possible that on this question it might be quicker for you, might be easier for you to do this using a different method, such as actually taking out the points and like setting up the slope, finding the slope between 2 points, subtracting them using the formula, then taking the slope and taking one of the points and plugging it in to find the y-intercept. And then once you've done that, you have the equation. And that's fine. I just want to show that this is an example, again, of a type of problem where if you have points like this, you can plug them into the equations or into the formulas and see, which formula, basically at least one or in this case 2 of the points work in to determine the correct answer. Now let's take a look at another example problem. This is from the College Board's Practice Test number 10. It's problem number 16. It is from the calculator section of that test. And basically what's going on here is you have two cities, city X and city Y. And so essentially city X had its population increase from like 2010 to 2015. City Y had its population decrease over that same time period. and they want to know if the population of city X was this amount in 2010, what was the population of city Y in 2010? So it's kind of like city X was here, then it went up, to 2015, whereas city Y was somewhere, and then it went down and ended up here in 2015, and then in 2015, they're both equal, they're both the same. So we can solve this using backsolving. Now, based on the picture I just drew, hopefully you recognize that the population of city Y in 2010 has to be more than 120,000, because 120,000 is what city X was in 2010. Then it increased to some higher number in 2015, and city Y basically came down from 2010 to 2015 to meet that number. So we can eliminate these first two answer choices right off the bat, but if you didn't recognize that or didn't notice that, that's fine. So here's how we could use backsolving for this. So let's say, okay, so city Y 2010 population 60,000. Okay, what does it tell us in the problem? From 2010 to 2015, the population decreased by 10%. All right, so basically what we're going to do now is we're going to take 60,000 and you could multiply it by 0.1, since that would be 10% of it, and then you could subtract that from 60,000. Okay, so its new population is going to be 54,000. Now, just before I continue, I just want to show you a little trick about percentages. So the calculations I just did were 2 steps long. I multiplied the 60,000 by 10% and then I subtracted from the original. You can do it all in just one step by just taking 60,000 and just multiplying it by 0.9 to get the same value. And that 0.9 comes from basically, 1 minus 0.1. And the 0.1 is the 10% just as a decimal. So it's like you start with 1, then if it's a decrease, you subtract off whatever the percentage is, and then whatever you're left with, you would just multiply, the original population or the original value by that number. But so we started city Y 2010 at 60,000. It's now going down to 2015 to 54,000. So next what we'd have to say is, okay, that's the population in 2015 of both city X and city Y, because it says that they're both the same. In 2015, populations were equal. So if city X's population was 54,000 in 2015, what was it in 2010? So now you go back here and you see, okay, city X increased by 20%. So the way we would calculate that, the way we would do that is we would take the 54,000, which is the 2015 total, and we would divide that by 1.2. Because I'm taking basically 1 and I'm adding 0.2 to it for the 20%. So from 2010 to 2015, there's a 20% increase. So it's like if we had the 2010 value, we'd multiply that by 1.2. Whereas if we have the 2015 or the ending value, we would divide it by 1.2 to get the original or starting value. So if you now do that on the calculator, then you get that the city Y value, city X 2010 population would be 45,000. Okay? However, that does not match what they tell us in the problem, which is right here, city X's population was 120,000. So that's what allows you to conclude or determine that this is wrong, because the 45,000 does not equal the given amount of 120,000. So it's a little bit long. It might be a little bit complicated to understand, dealing with percentages and how to move back and forth between an increase and a decrease, but I'll just show you how how we can confirm the correct answer and how it works out. So now let's take a look at answer choice C, 160,000. Okay, so we have 160,000 as a population of city Y. I just need to multiply that by 0.9 because it decreased by 10%, which is the same as multiplying by 0.9. So the 2015 population is now 144,000. Then that is the population of city X as well in 2015. And now what I need to do in order to figure out the population of city X in 2010 is just divide that by 1.2 to find out what it was before it increased 20%. So I get 120,000. That matches, that checks, what we're given in the problem. So the correct answer to this one is going to be letter C. Again, on a problem like this, it might not be any quicker for you to use back solving, depending on how comfortable or familiar you are with percentages and how to quickly calculate percentage increases and decreases. But just be aware, this is another example of a type of problem where you can use back solving. The last example I'm going to take a look at is practice test from practice test number 9. Again, this is a practice test the College Board has released. It's from section 4, the calculator section, and it's problem number 13. So here you have a problem, and this cargo helicopter basically is delivering two different types of packages, 100-pound and 120-pound packages. It has to carry at least 10 packages, but there's a weight restriction where it can only be 1,100 total pounds at most. It says, what's the maximum number of 120-pound packages it can carry? So all I'm going to do is start with the answer choices. So I'm going to say, okay, answer choice D, let's say it carries 620-pound packages. What is its total weight? 720 pounds. So let's say make 120 thing, 100 thing, how many? So 6. Therefore, it would carry at least 4 of the 100-pound packages because it has to carry at least 10. So that's where this 4 comes from. And now the total weight of that is going to be, so I just add that 720 to 4 times the 100-pound package is 1120. So my total weight, 1120. Notice that contradicts this thing in the problem which says it can only be at most 1100 pounds. So that answer is out. Now I would move on to answer choice C. And so now it would be basically 5 for 120 and 5 for 100. So now I could just type the whole thing in one step. 5 times 120 plus 5 times 100. That comes out to exactly 1100, which is acceptable because it says at most 1100. It doesn't say it needs to be less than it. So therefore, correct answer is just going to be letter C. And again, we did not have to set up any type of system of equations or system of inequalities or anything to solve this. We just took the answer choices, plugged them in to the calculator, did some basic calculations, and found out which answer choice was correct. Now, one last thing to be aware of regarding back solving. So back solving is not going to be able to solve, all of the problems that you may encounter on the SAT or even most of them. Instead, you should basically think of it as like, one tool kind of in your toolbox to help you solve problems as quickly and efficiently as possible. So you may only use it, a couple of times on a test, whether it's a practice test or an official test, but it's possible that it could help you answer some questions correctly that you otherwise either wouldn't know how to do, or it also may help you save time for harder questions down the line, because you might be able to solve a problem in a little bit quicker manner than solving it the traditional way, and you could use that extra time towards harder problems that you encounter in other parts of the test. So that was just a brief explanation of what back solving is and how you can use it. If you like this video, of course, please click the like button, subscribe to my channel, sign up for notifications as well. I'll have again more SAT related math content coming out in the near future. And if you have questions, comments, or anything to share, please leave them in the comments on the video down below.